Good evening and welcome to the Space Telescope Public Lecture Series. I'm your host, Dr. Frank Summers of the Office of Public Outreach, and it is my joy and pleasure to be your host each and every month. When you came in tonight, we had lithographs. Tonight's lithograph is a new one. It's an old image. But we realized we'd never put out a lithograph of this image. It's one of the classic images of the Orion Nebula from 2005. It was released on Hubble's 15th anniversary. And at the time, it was one of the largest mosaics we'd ever put together. It was some 300 million pixels. When we released it, Photoshop had a really hard time melding all those pixels together, right? It's kind of funny. We look at the things, we handle them all the time these days, these 100 million pixel images. You know, in 2005, handling a 300 million pixel image was not an easy thing to do. So if you want to learn about what's the science in it, turn over on the back and you can see it as star formation on a grand scale in the Orion Nebula. And for those of you online, we have the link, amazingspace.org, resource page 545. And you can download a PDF of it and look at it at your leisure. Our talk tonight, Your Place in the Stars from Amaya Moro-Martin. Next month, we have an astrophysicist guide to the film Deep Field, the Impossible Magnitude of Our Universe, by this crazy guy, Frank Summers. He'll probably just make it all up as he goes along because I know him. He just rambles on. In April, The Art and Science of Astronomical Image Processing from Joe DePasquale. A few years ago, how many people heard Zolt LeVay give a talk similar to this a couple of years ago? That was like 4 or 5 years ago. Joe is our new image processor. If you remember, Zolt retired last summer, at the end of last summer. And Joe is our new lead image processor, and he will give his take on it, on how he processes image. He also has significant experience doing X-ray astronomy. He came to us from the Chandra X-ray Observatory up in Boston, so he's got a really cool take on a lot of things. And in May, we have Jolene Karlberg talking. She did not give me a topic yet, but her specialty is red giant stars and extrasolar planets. So I'm thinking that will be her title, but we'll find out from her soon, real soon. And it will be posted on our website when we do have that. This is our website. If you just go to your favorite search engine and look for Space Telescope Public Lecture, you'll find this web page where we have the list of the upcoming talks over here on the right. On the left, we have the links to the webcasting, both live on STSCI webcasting and YouTube, as well as the archives where YouTube goes back to 2014. That's 5 years now. And STSAI goes all the way back to 2005. So that's almost 14 years of webcasting there for you. If you would like the monthly announcements, sign up for email there. Yes, that email, just to say it again, sign up at the website. Or if you don't want to do that, you can just write it down on a piece of paper and hand it to me at the end of the lecture, and I'll make sure you get on there. If you have comments and questions, you can send them to our email address, publiclecture@stsci.edu. Finally, if you're looking for us on social media, you will find Hubble, the James Webb Space Telescope, as well as the Space Telescope Science Institute on Facebook, Twitter, YouTube, and Instagram. You'll find me on Facebook and Twitter sometimes. Now, after the lecture, we often go observing, or sometimes go observing. Hasn't been very often lately. They tell me it is cloudy tonight, so we will not be having observing. If you would like to try and get to the observing, you can go to md.spacegrant.org, and you'll find the Maryland Space Grant Observatory open house page, and they have the observatory status there. They do observing every Friday night. Check it about 5 p.m. on Friday, and they'll let you know whether they're going to open on a Friday night. Okay? Now, our news from the universe for February 2019. Our first story is New Year, New Moon, and New Perspective. Now, New Year was last month, right? Not quite. Today is Chinese New Year, or The year of the pig, so Happy New Year. As an astronomer, I don't like to think of this as Chinese New Year because the Chinese use the Gregorian calendar too. It's the traditional Chinese or it's the lunar calendar. Because this was the beginning of the lunar calendar, the Lunar New Year is today. Which means, of course, what? It's the start of a lunar cycle. So what phase is the moon in at the start of a cycle? It's in new moon. And it just so happens that yesterday, during new moon, the Chinese satellite, Longchang 2, took a picture of the moon during new moon. So when you take a picture, can we get the house lights down a bit? There's too much scattered light on this. There you go. Now you're starting to see it better. So what are you seeing when you're seeing the moon? What is lit at new moon? The far side. There is no dark side to the moon. The dark side of the moon is night, okay? So when we look at the moon during new moon, we only see the dark side, okay? All right, that's the near side of the moon. But the far side, of course, is fully lit. So this satellite is orbiting around the moon and is able to take a picture of the full moon, but it's of the dark side, okay? Of the far side. You guys are messing me up. All right, of the far side of the moon in full moon, okay? Whenever you and I from Earth see the full moon, it's always the near side at full moon, right? Okay, this is a fully lit far side of the moon. However, it's a really cooler picture than you might think it is because 6 billion people photobombed this image. I covered it up and now I reveal, there it is. They got a picture of the full moon of showing the far side and Earth in the background, okay? So this is kind of cool. So, do you have a question?
So this is the side we never see, is that correct?
Yes, this is the side we never see. Okay, because the moon is tidally locked, so we only see the same side. As it orbits, it always shows the same side to Earth, right? Okay, so this backside of the far side is never seen when you're on Earth. You actually have to get off Earth to see it. So we never saw the far side until we went into space. Okay, so that's a cool thing. Other question?
Any reason why there's so fewer craters on this side than on the one?
Well, actually, there's more craters on this side. What there aren't are the big mare. Okay, in detail, this is but first of all, this is a really, really low resolution camera. Okay, it's a webcam basically at best. All right, this is not a scientific instrument. Okay, this is just a webcam, and I think the whole resolution of this photo is 640 by 480. Okay, so it's not even a good webcam. All right, but in detail, there's a ton more craters on the far side. Whereas on the near side, we had the huge impacts that had the mare spread out and the lava filled in to create the big, large impact craters. Okay? Is that a question over there? Same question. Okay. Yeah. Unfortunately, if you see a Clementine image of the far side of the moon, it's got tons and tons of craters. Okay, and this is actually a much more detailed in the cratering. Okay. Last question.
The dark spot, is that any significance? Is that okay?
All right, so the dark spot up top here, all right? So the dark spot up top here, that would be where there was a significant impact that smashed through the crust and then the lava welled up and filled it in, okay? Just like you see on the near side, you see some really big ones of the Luna Mare, or Maria, right? The seas, quote, quote, of the moon. These are actually places where the lava from the inside welled up and filled in and made it smooth and actually erased the craters that were there before. Okay? All right. Our second story, a 500 megapixel view of the Triangulum Galaxy. I was speaking about the Orion Nebula image being 300 megapixels. Wow, we have a 500 megapixel view. Okay, so let's set this up for you. This is a pan of the night sky showing our Milky Way galaxy. Our Milky Way is a large galaxy. And in the local group, there are 3 respectable galaxies and a lot of, flotsam and jetsam dwarf galaxies, okay? You can see 2 of the flotsam and jetsam dwarf galaxies over here on the right. These are the large and small Magellanic Clouds. You can see the other large galaxy over here on the left. This is the Andromeda Galaxy. So the second large galaxy in our local group is the Andromeda Galaxy. It's about the same size as the Milky Way, perhaps about 10-15% larger from most estimates. And about 10 years ago, we did a very large mosaic panning through the Andromeda Galaxy, and it was called the Panchromatic Hubble Andromeda Treasury Program. Just because the PI wanted to be able to spell out PHAT. Oh, it's fat. All right. So the Panchromatic Hubble Andromeda Treasury Program was the largest image mosaic we've ever produced. Okay. It was. Let's see. If I go to the next slide, here you go. Here it is. Here's the fat image. Okay. It was like 52,000 pixels this way, by like 20,000 pixels this way. This was definitely, the full image was like 1 billion pixels here. All right. And this was like 420 observations with Hubble, different fields in the observation, amazing, huge. And that's why it's a treasury program, because these were special programs given a lot of Hubble time to do really big things. Well, this was a huge boon for stellar astronomy, because they could resolve hundreds of millions of stars in the Andromeda Galaxy and able to study the stellar populations going from the core of the galaxy out to the edge of the galaxy. So if that worked for the Andromeda Galaxy, let's apply it to the third largest galaxy in our local group, which is the Triangulum Galaxy. So this is a ground-based picture of the Triangulum Galaxy, and Hubble is going to do that same mosaicing field on this, and we covered approximately that much of the Triangulum Galaxy, and this 500 million pixel mosaic looks like that. And you say, well, that's not really cool. Well, you're seeing it on like 1 megapixel, okay? So the 500 megapixels aren't a thing. But just see, there's an incredible amount of detail. And let me, and so I think they probably considered calling it the Panchromatic Hubble Triangulum Treasury Program, but that would come out as So I'm just going to refer it to as the Hubble Triangulum Mosaic. No, they did not try to call it the PHTT. That's just me having fun here. The Hubble Triangulum Mosaic of all this stuff. And let's show you just how detailed it is. So here is the night sky. And if you didn't know, there's Triangulum Major and Triangulum Minor for constellations. And of course, here is our Triangulum Galaxy in the center. And watch how far we get to zoom in to see the full detail of the Hubble image. Yeah, we just keep going. And we keep going. Yeah. There you go. That we get to the detail of the Hubble image, okay?
My scope can't do it.
Your scope definitely can't do it, because you see all this blurry over here in the lower left corner? Yeah, that's what we're taking from the DSS survey, etc. And this is the Hubble image overlaid on top of it. And all of these stars you see here, they're not stars in the foreground. Those are stars in the Triangulum Galaxy, okay? We are resolving individual stars in the Triangulum Galaxy. They tell me there are more than 25 million individual stars in this mosaic. So here's the mosaic. This up here is NGC 604, one of the largest star-forming regions in the local group. And you can see what incredible detail Hubble can get in that, and all the individual stars they can see. Look at this globular cluster, okay? That's the green box. So that's right here. That's a globular cluster that we're seeing in a galaxy 3 million light years away, okay? There are, of course, a few foreground stars here. That's the blue box, so right here. And there are also background galaxies, all right? Then this red box here. So the Triangulum Galaxy is not opaque, it is somewhat transparent, so we can see through it and see some of the background galaxies. Now they're going to do again with the Triangulum galaxy the same star formation and stellar population studies that they did with the Andromeda galaxy. But as evidenced by NGC 604, there is significantly more star formation per unit mass in the Triangulum galaxy. So they're able to study more of these bursting star forming regions. The star formation rate in the Triangulum is 10 times the star formation rate in the Andromeda galaxy. So they're able to study in great detail the stellar populations in a galaxy with much more star formation, which will extend the study into new realms. So we have another 500 megapixel image. Oh, piece of cake, right? These days, yeah, even these are still difficult to handle. But by taking Hubble and spreading it over a lot of fields, you can get a lot of images. Let me just say one thing, okay? That we have on the books for the next decade a telescope that has the same resolution as Hubble, but 100 times the field of view. All right? In the next decade, it's an infrared one, okay? But in the next decade, we'll be able to take images like this routinely, not using hundreds of individual pointings, but using 5, 10 individual pointings. So we're looking towards, in the next decade, a great revolution in astronomy in terms of the amount of data that we're going to be able to handle with these 100 megapixel cameras on these on the variety of telescopes. So this is really cool. It's really great, but it just reminds me that in the future, this is going to be commonplace. And we're going to be able to get this type of stuff every day. So let's enjoy it and always look forward to the future. All right. That's our news for the universe for tonight. Our featured speaker tonight is Amaya Moro-Martin. She has been here at the Space Telescope Science Institute for 5 years, and she works in what's called the Science Missions Office. And where she specializes in working on the James Webb Space Telescope. Her science studies focus on debris disks, debris disks around stars. Of course, there is a little bit of debris in our own solar system, but most of the place where you would find debris disk is around newly formed stars, where there are planets forming, where planets have formed around other stars, looking for these disks and materials inside those stars. But today, she's going to talk about our place in the stars. So, ladies and gentlemen, Amaya Moro-Martin.
Thank you. Thank you very much. All right. Oops. The pressure. There you go. All right. So, okay. So to start with, I'm going to show you a short movie by Eric Wernquist, narrated by Carl Sagan, where you will see images of real sites of our solar system that are recreated from real photographs and real data obtained by NASA. This short movie begins with an image of some nomads that are walking on a valley on Earth, probably around the Neolithic, around the time that agriculture was invented. And let's see if it plays. There you go. Oh.
That's here.
Oh. Whoa. What do you mean? That's here, that's home. I think it went to the last piece of it. There you go. There. So they are walking on a valley on Earth just after sunset. And in the horizon, they can see Mercury, Venus, Mars, and up there, Jupiter and Saturn. And the title of the movie is Wanderers, which is the same name that the ancient Greeks gave to the planets. To these nomads, these planets were indistinguishable from the stars, except that they were brighter. Until someone stopped to observe them carefully, recording their positions every night, and realized that they move very different from the stars. They start moving in one direction, and then they start going in a retrograde direction, and then they keep going in the same direction. And this observation was done more than 2,000 years ago by the ancient Greeks, or maybe even earlier by the ancient Egyptians. And this is why the ancient Greeks called these stars, they call them wandering stars, because they seem to wander in the sky, and the word planet comes from the Greek planetes, that means wanderer. The title of the movie does not refer to the planets. It refers to our quest as humans to understand, to discover, to explore the unknown. And in doing so, many times we challenge widely accepted ideas. Take the planet's wandering movement as an example. That movement drove many people crazy because they just couldn't figure out why the planets would do that. And they could not understand it because the widely accepted view was that the Earth was at the center of the universe. But if you change that view, that mindset that everybody believes in, and you accept that the Earth is not at the center of the universe, but that moves around the sun, as Copernicus suggested more than 400 years ago, then the movement of the planets could be understood. But challenging widely accepted ideas is not easy. This is Galileo Galilei. You all know him. This is the Italian astronomer that ran into a lot of trouble for defending that the Earth was moving around the sun. And he was convinced this was the case because he had made careful observations using a telescope. He was the first astronomer to do so. And he had also discovered that there were fainter planets that were orbiting around Jupiter. So if there were fainting planets orbiting around Jupiter, why couldn't the brighter planets orbit around the sun? And Galileo got into a lot of trouble, as I said, for defending this idea and for claiming the Earth was not fixed at the center of the universe. And he ended under house arrest because the Inquisition accused him. And the story goes that when he was released, he looked to the sky, he looked down and he stamped his foot and he said, and yet it moves. Because he wouldn't surrender his idea because it was based on evidence. This is Giordano Bruno, another astronomer, scientist and philosopher that lived before Galileo, that also got into a lot of trouble for arguing that in an infinite universe in which all stars are surrounded by their own planetary systems, the most logical thing will be for other worlds like the Earth to exist. And if so, they would harbor life. Think that this was a statement made more than 400 years ago. This is mind-blowing. And his views, of course, were considered heretical at the time, and he was on trial and he was burned to death. But he stayed true to his arguments, and one of the quotes that people attribute to him is that truth that does not change because it is or it is not believed by a majority of the people. And guess what? The other day, while I was preparing these slides, I took a break to browse one of the issues from Nature, the Nature magazine that I get on the mail every week, and I found this letter. This is a letter written by Galileo in 1613, and historians knew it existed, but it was thought to be lost, and it was discovered by chance this last August in London in the archives of the Royal Society. And according to Nature, this is the letter where Galileo first defends that scientific research should be free from theological doctrine. And this letter that launched one of science history's most famous battles is one of the first secular manifestos about the freedom of science. So this is a very powerful letter that fortunately now, we know we have it now. It was thought it was lost. And when I saw this, I felt that history was sending us a message from a time long past to remind us what is at stake today. Because we live in a paradoxical time in which even though science and technology are omnipresent in our everyday life, and thanks to them, many of us enjoy a standard of living that has never been so high, there is a growing gap between science and society, as it can be seen, for example, in the questioning of vaccines and climate change, the rise of alternative medicine, and even the questioning of evolution. And this is so because also thanks to science and technology, never before we have had access to so much information, but also to so much misinformation. And We live in a post-truth world, unfortunately, where ideological affirmations are commonly presented as equivalent to those based on evidence. And this letter, I thought, was a reminder of the extraordinary importance of science to help citizens to develop the ability to think critically based on evidence, which is the key of all scientific activity, of course, and which is an ability that can be applied to all aspects of our life and can help us become better informed, less manipulable, and demand an evidence-based policy. And this is so important nowadays. But let's get back to the short film I promised to show you. This film talks about the need of the human being to explore the unknown, because that curiosity is precisely one of the human being's most characteristic traits. That curiosity is what centuries ago made us climb to the top of the highest mountains to see horizons that nobody has ever seen, or make us dive into the deepest trenches of the ocean to witness the dark alien of the abyss. And it is the same quest that made us search for answers for what we don't understand, like the movement of the planets in the sky. It is the same curiosity that allows us to, little by little, make sense of the world we live in, even if the findings challenge our previous beliefs, like the story of Galileo. And as I said, the short movie begins with nomads that are looking at the planets, and then the movie makes a big leap in time to show us a snapshot of the future, where you can see a spacecraft moving away from the Earth, and on board this spacecraft, maybe the first explorers of the solar system. And what the short film does is to narrate with images recreated on real data. The story of these nomads, these wanderers of the future, these pioneers exploring not new continents or new oceans, but new worlds. And now we see the movie.
For all its material advantages, the sedentary life has left us edgy, unfulfilled. Even after 400 generations in villages and cities, we haven't forgotten. The open road still softly calls, like a nearly forgotten song of childhood. We invest far-off places with a certain romance. The appeal, I suspect, has been meticulously crafted by natural selection as an essential element in our survival. Long summers, mild winters, rich harvests, plentiful game. None of that lasts forever. Your own life, or your band's, or even your species, might be moved to a restless few, drawn by a craving they can hardly articulate or understand, to undiscovered lands and new worlds. Moby Dick spoke for wanderers in all epochs and meridians. He said, I am tormented with an everlasting itch for things remote. I love to sail forbidden seas. Maybe it's a little early. Maybe the time is not quite yet. But those are the worlds, promising untold opportunities, beckon. Silently, they ordered the sun,
breathtaking. So why are we fascinated by these worlds? Because we have found through careful observation that they might harbor the conditions to sustain life. We haven't found life yet, but knowing that the conditions for life may exist in these worlds is extraordinarily exciting. So this is an image of Europa that you saw in the film. It shows explorers. You see the explorers here. And they're walking on its icy surface. Europa is one of the great moons of Jupiter, shown here in the horizon. This is Jupiter, right? And Europa is a little smaller than the moon and is made of silicates with a core made of iron and nickel, just like the Earth. But Europa has a thick frozen crust that is several kilometers in thick, that is full of cracks. And there is evidence that under this ice there is a liquid ocean that is estimated to harbor twice as much water as the oceans of the Earth. And it is also believed that Europa has a tenuous atmosphere of oxygen. How can there be liquid water inside Europa if it's so far from the sun, right? This is what we call the habitable zone, is the area in the solar system where liquid water can exist on the surface. Only 2 planets are in this habitable zone in the solar system, Mars and the Earth. And if you go too close in, it's too hot and the water will evaporate. And if you go too far out, it's too cold and the water will be ice. But liquid water can exist in Europa because it is very close to Jupiter, and its enormous gravity produces tidal forces inside Europa that are a source of energy. These tidal forces are similar to those created by the moon on Earth's ocean that are responsible for the ocean tides. So these tides in Europa are much stronger because Jupiter is very massive, and they're so strong that they can cause geological activity similar to that of the tectonic plates on Earth. And this creates these cracks in the icy surface of Europa. And through these cracks, it seems that there is material from the frozen surface that sinks to the liquid ocean underneath, and the other way around, material from the liquid ocean underneath that rises to the surface. And the reason why we know this is happening, even though we haven't actually sent any robotic explorers there or any robotic explorers there, is because we think that this brownish material that you see in the cracks is the salt that is coming from the liquid ocean underneath. And we know this because when you put this type of salt in a chamber and you put it under the temperature and the pressure that is in Europa, it comes out of a similar color as the one that we see in the cracks of Europa. Both the existence of liquid water in Europa and of that flow of material between the icy surface and the liquid water underneath are very interested in the context of whether Europa could harbor life. And it has been speculated that there may be hydrothermal vents in that ocean of Europa, similar to the ones we have on Earth. And on Earth, these vents are teeming with life, thanks to the heat exchange and the exchange of chemical compounds. So Europa is also very interesting because it is very likely that it has jets of material that are being launched into space hundreds of kilometers high, and similar to those that have been observed in another moon, in Enceladus, one of Saturn's moons. And this is an image of those jets of material taken with the Hubble Space Telescope by one of our researchers. And this is Enceladus. So these are the jets in Enceladus. This is not a recreated image, this is a real image. Enceladus also have an icy surface, and the jets are produced by geysers that form in the cracks that throw jets of water vapor into space. And this water vapor then falls in the form of snow to the surface. A fraction of that material escape and becomes Saturn's ring. And these geysers are one of the indications that, like Europa, there is liquid ocean, there is a liquid water ocean under the surface of Enceladus, also making it a very interesting target for the search of life. And the existence of these jets in Enceladus and in Europa is particularly interesting because imagine trying to design experiments that actually look for that life. In Europa, for example, it will have to drill through 10 kilometers of ice, and this is very difficult to do on Earth. So imagine bringing all that equipment to do that drilling in Europa is very difficult, right? But if there are jets there, it's much easier to design a space mission, like the one you see here, that flies through those jets. And in this spacecraft, you could have instruments able to analyze the material coming out of the jet. and which is a sample of the material that exists in the ocean, and you can look for signs of life there. So no need to drill. And in fact, scientists realized a few months ago that a spacecraft, 20 years ago, a spacecraft named Galileo, is thought to accidentally have flown over one of the jets in Europa. At the time, we didn't know these jets existed. Now we do, and Galileo shows some anomalies that now can be explained by the presence of these jets. And there is indeed a mission called Europa Clipper that NASA is planning to launch around 2023 that will be designed to do exactly that, to fly through the jets in Europa and to analyze the material that is coming from those jets, searching for life. Titan, here's another image that we saw in the short film. It shows explorers that are flying over the lakes of Titan. Titan is a giant moon of Saturn that is larger than the planet Mercury, about half the size of the Earth. It's mainly composed of silicates and water, and is the only moon known to have a dense atmosphere, composed mainly of nitrogen, like the atmosphere of the Earth, and a bit of methane and other hydrocarbons. Titan has an average temperature of minus 290 Fahrenheit, minus 180 degrees. And at that temperature, the methane can be in solid, liquid, or gaseous state, just like the water on Earth. So instead of having a water cycle, like in the Earth, we have a methane cycle, and where the methane evaporates, rises into the atmosphere, forms the clouds, rains down, and forms rivers and lakes. Here you have here you have the reflection in one of those lakes, and here you have one of those lakes where you see the coast. You can see the coast, how it changes as the liquid level rises and falls. It's actually is actually the only place in addition to the Earth, where in the solar system, where you can have lakes, and you can have archipelagos, and you can have islands. And there is also wind in Titan that forms dunes, but the grains in the dunes are not made of silicates like in the Earth. They're probably made of complex organic compounds. So, and on Titan, it is possible that there are also volcanoes, but the lava would be made of water and ammonia instead of silicates like in the Earth. And the energy source that will drive the volcanoes will be not only the radioactive elements like in the Earth, but also the tidal forces caused by Saturn, that deforms the planet producing heat. And it has also been speculated that there is liquid water under the icy surface. So the presence of all these complex organic compounds, of lakes, of an ocean under the surface, of cryovolcanism, of an exchange of chemical compounds between the atmosphere, the surface, the lake, all this makes Titan an extraordinarily interesting place to search for life. And people have done experiments in the lab where in the chamber they put the gases that they think are in the atmosphere on Titan, and they put it at the temperature and the pressure that they think are on Titan, and then they heat everything, and what they find is very interesting. They find that nucleotide bases form, which are part of our DNA and RNA, the building blocks of life. They also find that amino acids form that are essential ingredients of proteins. And this is really extraordinary because it means that even in the absence of water, these elements that are so important for life can emerge from simpler organic molecules. In fact, it is possible that the atmosphere of Titan is very similar to the atmosphere that we think the primitive Earth had when life first arose on our planet. And this is why Titan is such an extraordinary laboratory to study the conditions that could have given rise to life on Earth. And if there is an ocean beneath the surface of Titan, it's possible that it could harbor life today that could survive thanks to the transfer of chemical compounds and heat between the ocean and the surface. So, if life were to exist in Titan or Enceladus or in Europa, it will be under very extreme conditions. But the truth is that life on Earth can survive under very extreme conditions. For example, in these water lakes, in these geysers in Yellowstone, life can survive in extreme heat, in extremely cold environments, and also in very acid environments like those inside the battery. And if life were to exist in Titan, Europa, or Enceladus, or somewhere else, it would be probably very different from that on Earth. For example, it has been speculated that life in the shallow methane lakes of Titan, instead of breathing oxygen, will breathe hydrogen. And instead of exhaling CO2, it will exhale methane. And instead of using water as a solvent, it will use methane, liquid methane. The bottom line is that we need to open up our mind regarding the search for life, because what is out there is probably very different from what we know, and we might not discover it if we are not ready for those surprises. So the search for life needs a mindset change, like the one that was required to understand the movement of the planets or the theory of evolution. So where do we come from? How did life on Earth originate? Our species is a very curious one, and this very question has followed us for thousands of years. At first, we have tried to address it through stories and myths, because that was the best way we had to make sense of what we did not understand. And later, we have been able to address it through careful observation of nature, by carefully collecting the evidence, testing many hypotheses, checking what it works, what it doesn't work. And this very question regarding the origin of life has also sent women and men to seek for our origins in the remotest corners of our planet and even beyond. So where do we come from? Did life on Earth originate in our planet, or did it originate somewhere else? If there is life on other planets or other moons in our solar system, or in other planets in nearby stars, could it have a common origin to ours, or did it emerge independently? Could life on Earth, or the building blocks of life, have spread to other planets and other moons, or vice versa? So look at this rock. This is a meteorite. Meteorites are extremely valuable because they can teach us a lot about our origins. A few years ago, in 2011, after analyzing rocks like this in the lab, people found that they contain some of the components of DNA and RNA. And as you know, these are the building blocks of life. They are like life's Legos. And people discovered that these complex organic molecules, adenine, guanine, can form in space. It was also recently discovered that the dust that exists in space contains complex organic molecules like sugar that are also necessary for the formation of RNA. And of course, the joke when this was discovered is that the next thing astronomers will be seeking is caffeine. And this was found by analyzing the light that the dust emits. And what people realize is that these sugars can form very rapidly around stars, even before the planets form. And this is very exciting because it means that once the planets form, these molecules can fall on the planets and facilitate the emergence of life. So how do stars and planets form? So stars are born in clouds of gas and dust. One region of the cloud gets very dense and very hot and collapses under its own gravity. And at some point, the star ignites, and this is when the star is born. Around these protostars, there is an envelope of gas and dust, and because everything is rotating, because of conservation of angular momentum, you form a disk. So this is what we call a protoplanetary disk. So some of the gas and the dust in the star is accreted to the star, and on some of the gas and the dust in the disk is accreted to the star, and some other part of the material is ejected in these jets. But let's see what happens to the gas and dust that stays in the disk, that remains in the disk. The disk is very dense, and the dust particles are colliding with each other. And frequently, this collision makes the particles break into smaller pieces, or they bounce, but in many times they stick together. And when they stick together, they start forming larger and larger aggregates. They first form like pebble size, then it's like boulder size, then it's like asteroid type size, until they form the planets. And also they form planets much more massive than the Earth, like around 10 times the mass of the Earth. And at that point, these planets are sufficiently massive that they start attracting the gas in the disk to form giant atmospheres, like the planet Jupiter or the planet Saturn. And later, when the star dies, a part of that material is returned to space and to become part of the new clouds of dust and gas that from where new stars will be born. So all this material is recycled. And that is how some of those complex organic molecules that are so interesting for life, that can form in space or around other dying stars, can get to the young forming planets. So, and here you have real images that capture how stars and planets form. This is an image of the clouds of gas and dust where the planets and the stars are born. This is, of course, taken with Hubble. This is another image taken with Hubble of the protostars and their disks where the planets will be born, seen here in silhouette. So here you have the disk, and here you have the newborn star, and here you see it more face on. Here you see it edge on. And this is a disk where the large planets have likely formed already, have begun to accrete the gas in the disk. So these dark areas is all the gas-depleted regions in the disk that has already accreted into the atmosphere of the forming planets. And here is a family photo of baby planetary systems being born. So here it's like, oh, they're babies. Some of them are face-on. Some of them are edge-on, and some of them have this cometary elongated shape because they happen to be very close to a very massive star that is blowing away with its strong wind some of the material in the disk. And this is a family picture of the elderly showing the spectacular ways in which some stars, when they become very old, return material to space for its recycling. Another beautiful Hubble image. So I have told you that there are very interesting molecules that form in space around this type of stars that can get to the young planets and maybe help life to emerge. And another molecule that got here from space that is very important for life is water. And when the Earth was formed, it was very dry and very hot. It was more than 1,000 Celsius, so around 2,000 Fahrenheit. Now it's nice and cool, and about 3/4 of the surface are covered by liquid water. But still, if you consider the bulk of the planet, the Earth is very dry. But where did all this water in the surface come from? After analyzing different types of comets and asteroids in our solar system, people realized that they may come from these objects that fell on the Earth when the Earth was very young. And we know this by analyzing the type of water that is detected in asteroids and comets and comparing it to the water that is on Earth. Because water, as you know, is made of 2 atoms of hydrogen and 1 atom of oxygen. But sometimes you have an extra neutron in the hydrogen. Instead of the standard hydrogen, you have deuterium. And that ratio of how many water molecules present that extra neutron compared to so you compare that ratio of the water we have on Earth to that found in asteroids and comets. That ratio is very similar to what we find in this type of solar system objects. So it is very possible that the water in our planet comes from them. So the next time you are on the beach, think that water have not always been there, that it came from outer space, that it connects you to the universe. And yes, as it rained on Earth, it also did it on other planets around other stars, where it may have created a fantastic landscape enjoyed by other wonderful creators like you. So let's look at some numbers. So when did the Earth form and when did it meet the necessary conditions for life to emerge? So this is, for perspective, this is how old the sun, the solar system is. This is how old the Earth is. This is how old we think life is, how old are animals, how old are mammals, and how old are humans. And to be honest, I had to make this thicker than I should, because otherwise you wouldn't see it. It's really mind-blowing. So let's talk a bit about how do we know this part, the top part. So how do we know, for example, how old is the solar system? We can measure it in the lab. How old are the oldest meteorites? This is a type of meteorite called sea chondrites, and they have these white inclusions here. These are called calcium aluminium inclusions because they are made out of calcium and aluminium, these white specks here. And if you analyze them, they are 4,570 million years old. And it is thought that they form when the gas in that protoplanetary disk that I showed you before that surrounded the young sun condensed, like when water vapor condenses into clouds, forming the raindrops. And we think this is how these solids form. And it is thought that these are the oldest solids in the solar system. So we think the sun is that old, around 4,570 million years. So we think that 43 million years after the solar system formed, the young Earth collided with a planet the size of Mars, and out of the debris of that collision, the moon formed. And we can date that because we can date the rocks in the moon. And if you date them using a hafnium tungsten chronometry of the lunar magma, it tells you that they are very old. They form only 43 million years after the sun formed. But the young Earth was not a habitable planet because it was all covered by lava. So when did the surface of the Earth cool down? So it is thought that this happened 70 million years after the solar system formed, and we know this because we can measure the ages of microscopic minerals called zircons. And this quartzite conglomerate found in Australia has these zircons, and people think these zircons form from the crystallization of magma that contained molten earth crust that was being recycled and that had been in contact with water near the surface. So that's the critical part, that zircons are evidence of water near the surface. And other zircons date the presence of liquid water on Earth between 164 million years and 280 million years after the solar system formed. So pretty fast. So once the Earth cooled down and there was liquid water on the surface, how long took life to emerge? Well, we don't really know, but studies show that it could have happened very quickly, between 0.3 and 3 million years. It could have happened. If life arose in shallow pools like this one, where you see these stromatolite microbial carpets. In fact, the oldest undisputable evidence of life on Earth come precisely from fossils this is like a cross-section, that look exactly like this. And they are this old. They are 1,570 million years old. So not million years old, but million years after the solar system formed. So, or it could be that life arose even faster in hydrothermal vents like these ones found at the bottom of the ocean. And actually the oldest evidence of life, this is more disputed, maybe these fossils, these microorganisms here that are much older than the stromatolites that I showed you earlier, and that are found in rocks that form between 290 and 800 million years after the solar system formed. So very quick. So as you can see, we are not certain when life arose on this planet and in what type of environment, and we don't know either what was the role of extraterrestrial material falling on Earth, if it provided the building blocks of life in addition to water. But the next time your child or your grandchild bends down to pick up some pebbles and you hear yourself saying, "Don't bring that home," like I sometimes say with my 6 and my 2-year-old daughters, Luna and Estella, fill up their pockets with rocks gathered even from the parking lot, and then I hear those pebbles in the washing machine. So remember that those rocks are a real treat for the intriguing mind of the inquiring mind of a child, that they are collecting and inspecting the evidence, and that the answer to those existential questions regarding an origin probably is locked in a handful of rocks that is waiting to be discovered by them. And the short film, as the short films show, people have long dreamed about the possibility of visiting other planets, even setting up colonies there. Here are some advertisements from NASA's exoplanet Moro, a fictional travel agency for travelers to visit recently discovered exoplanets. These, of course, are fictional. You see Enceladus, it says, visit beautiful southern Enceladus, more than 100 breathtaking geysers. You have Titan. It says, ride the tides throughout the throat of Kraken. Here you see Kepler 16b, where your shadow always have a company because it's a double star, right? Here you have TRAPPIST, planet hop in TRAPPIST, because you have all these, planets. So, and here you have super jump, right, in an atmosphere, experience the gravity of HD 4370G, a super Earth. So these posters are of course made to make you laugh and to make you dream, but also to make you reflect on the extraordinarily diverse how extraordinarily diverse planetary systems are, and the extraordinarily diverse life forms that they could harbor. But I would like to finish this talk with some wise words from Carl Sagan, because this human curiosity of ours that has allowed us to better understand our place in the universe, to learn how stars and planets form, and how diverse planetary systems and life can be, this human curiosity that has allowed us to adapt to the world around us so we can live in it more comfortably. This curiosity of ours has also allowed us to adapt the world to our own needs. And this comes with a responsibility to protect the Earth and also the species that inhabit it, to live a sustainable life that doesn't exhaust the Earth's resources, and to protect the environment. And this is what Carl Sagan talks about in this short movie, because so far, no matter what our dreams are, the Earth is the only planet we can live in.
All right. Do we have any questions for our speaker? Peter? I don't know. We'll see.
Are you familiar with the film Europa Report?
No?
Oh, really?
I should. Okay.
Good.
Okay. All right.
The other question is, there are some who think that microbial life could have developed on. Oh, thank you.
Audience, please.
Yeah. There are some who say that microbial life could have formed on Mars, perhaps deep underground, before it formed on Earth. Do you have any comments on that?
Yes. No, I don't have any deep comments, but absolutely. And I think they are actively searching for signs that to see if that is still the case, if it still, could survive there. And it's so close, right? And it's just mind blowing that it's actually a real possibility that this could happen. Yes. And also another thing, there is a lot of material that is exchanged between the planets in the solar system, a lot of solid material. So, if that was the case, there are meteorites that come from Mars that could have harbored, this type of microorganisms. So, yeah.
Yes, I noticed in the pictures that you have of Europa and Titan how pristine and clear it was. You could actually see right down there. And then when you had a picture of on the Earth, that there were clouds on the Earth. That makes me think, do these other planets or moons have any kind of atmospheres?
Yes.
And is the atmosphere necessary for life to develop?
Well, as I said, you need a mindset change, right? So I would say yes, that you need an atmosphere. If you have an ocean, you will have an atmosphere, and you need liquid water. So probably yes, you need an atmosphere So yes, I would say yes, you need an atmosphere. And Titan has an atmosphere, Mars has an atmosphere, Enceladus has a thin atmosphere as well. So yeah, they all have atmospheres, but like you saw, Titan has beautiful clouds. You saw the image of the clouds in Titan. That it really, this image, maybe you thought that it was an image of the Earth, but this is actually an image of Titan. It's a real image of Titan. This is a real image of Titan, and that's an image of this type of clouds in the Earth. So, and these are real images. These are real photographs. So.
But of course, the composition of the atmosphere makes
it's very different.
Difference.
Oh yes, the composition is very different, right?
You've got, 97% carbon dioxide on Venus.
And this is
almost all nitrogen.
Nitrogen plus methane.
And
right.
if I remember from my coursework, oxygen in the early Earth atmosphere would have been bad for the development of life.
Right.
Because oxygen didn't develop until about 2 billion years ago.
Thanks to life, right? So, yeah.
All right, microphone over to here.
So this, say our moon is tidally locked, but these other bodies aren't necessarily, and that's providing the heating. Anything about, I know they're covered with ice. Is there anything like high or low tides with the ice, and is that visible in any photographs?
No, I think that you cannot see the tides on the ice, but you can see evidence that there is these tidal stresses that are a source of heat. And this is what is producing the cryovolcanism that we think it is taking place in some of these objects. This is what is producing the volcanism on Io. You see, volcanoes erupting on Io, and it is because of these tidal forces created by Jupiter. And so that's a very significant source of energy for these moons.
And just to clarify some things for the online audience, there was a chat about volcanism, and they were assuming it was volcanism like here on Earth. But you said specifically, just to repeat, cryovolcanism, which occurs at extremely cold temperatures.
Right.
Other questions? Herman's got a question in the back there. Hold on, Herman. We got to get the microphone up to you.
Sometimes the online audience likes to know too.
Was the very earliest life on Earth based on DNA and RNA? The very earliest life on Earth. Was it based on DNA and RNA?
You got me there. I work on. I think it was based on DNA, right?
I didn't get that. I'm sorry.
Can't imagine it wouldn't be.
Right.
But it's not my specialty either.
Yeah. Sorry. I work at the other side. My expertise is at the other side of the spectrum, is in forming the planets, destroying them.
I have a question. Excellent presentation, but a lot of exciting worlds out there. And I don't want to wait. Is it a funding thing from NASA, or is it a lack of technology, or why we have to wait to 2023? And do you envision continued collaboration with other country space agencies and private investment? I mean, it sounds really exciting. I don't want to wait till 2023.
Yeah, but it's a balance, right? Because it's a lot of money, right? It's a question of funding. Of course, it's limited by funding. We have a lot of ideas, but in some cases, it's technology development, right? I mean, we would love to send explorers to Mars, but there are actual limitations. It's not only expensive, but there are actual limitations. Sending human exploration has actual limitations. So we, here at this institute, we are working on a wonderful space telescope that will be overlapping with Hubble, the James Webb Space Telescope, but this is technologically very challenging. So it's both. You are limited by technology, the need of technology development, but also the need to have a sustainable budget, right? So, but waiting to 2023 is not that long. But
I remember Viking in the 80s, and they had the same kind of experiments looking for colorimetric changes with media on early Mars.
On early Mars, right? Yeah.
Flying through the cell, it seems like.
But
the Viking program in the 80s for the online audience.
Oh, yes.
Okay, so the online audience was spurred by the mention of cryovolcanism, and they wanted to know how prevalent is cryovolcanism in the solar system. So we've got Io. We've seen it. We've seen evidence of it on Pluto, right?
On Pluto, on Europa, on Enceladus.
On
right?
Enceladus,
so
okay.
At least those, right? For sure.
There's at least several places where. And how well do we understand cryovolcanism? Because when I went to graduate school, there was no section on cryovolcanism that I remember taking.
I don't know. It's a.
I mean, I know that the prevalence of it on Pluto was rather surprising, especially the very tall ice mountains.
Yes.
So I guess there's still plenty to learn in the solar system.
Yes, absolutely. The new horizon really opened a new world to us. Yes.
Okay, we got a question up there. I saw this.
Since you mentioned the James Webb Telescope, and you work on that project, could you give us an update on what is the next years for that project too?
Oh yeah, we are launching in probably official launch date is March 2021. So it's coming up, and we are getting ready. Yeah. It's coming up. There is already approved observing proposals. There is already grant money flowing into the proposers, and they're getting ready for it. So yeah, this building is boiling with ideas of how to make it work, and it will be wonderful. Yeah, so it's coming up.
We only get one shot at this one. So get it right the first time.
Yes, that too.
I'm sorry, could you please refresh my memory as to what cryovolcanism is?
Cryovolcanism.
Cryo, whatever.
Volcanic activity at extremely low temperatures, cryogenic temperatures.
Right, and generally the heat source will be tidal heating, right?
Does Io have that, or is Io hot?
Io, okay, sorry.
Does
Io
Io
is-
have
is-
cryovolcanism as well?
For the all my elements, sorry.
Yes. Oh,
What's the future of the Hubble telescope then when Webb starts to operate?
sorry. There was yes. There was I thought you wanted to comment on that. Yes.
What's the future of the Hubble telescope when James Webb is flying?
Oh, Hubble will keep operating. Hubble can operate for many years from now, so we have it. We are planning a long future for Hubble, and it will be wonderful to have both. That we will have both telescope operated simultaneously because they can complement each other in a wonderful way. Yes. So.
Do you want to say more about the cryovolcanism on Io?
On Io. So on Io, is it cryovolcanism? I think
it's sulfur dioxide. I know that much. I don't know what temperature that would.
Yeah, I don't know either. If it's, I will say it's not. But I don't know. I don't know.
The surface of Io is completely ice covered.
It's ice, right? So it's So I don't know.
All right. Question over here.
Given the evidence and everything that we know right now, which do you feel personally? Which do you feel out of the three candidates is the best? Has the best chance for some kind of life? Enceladus, Titan, Europa. Which do you think?
Well, I would say Titan, but maybe I'm biased because I spent, many years at the University of Arizona, and that's, there is big Titan experts in there. So we heard all these wonderful things about Titan, but I think we will have much more to say about this when Europa Clipper gets to Europa, right? The first of these planets, mini planets that we will explore is Europa. So there are no plans to explore Titan in the near future. So we'll cross our fingers for Europa. Yeah.
All right. Any last questions here? All right. If not, next month we will have my talk on the film Deep Field, The Impossible Magnitude of Our Universe. It will include a talk as well as a showing of the film. But until then, let's give Amaya a big round of applause.